Hello, welcome to today's webinar, The Basics of Color Measurement Instrumentation. This is the second webinar of a six-part series designed to help print and packaging professionals tackle color accuracy. My name is Ed Hattenberger, Senior Color Scientist at X-Rite, and I will be leading today's session. Before we begin, if you have any questions throughout the presentation, please use the chat function to submit them, and I will do my best to answer as many as I can at the end. If we run out of time, an X-Rite team member will contact you afterward. So let's get started. There are many different options for measuring color in print, and each is optimized for specific uses. Selecting the right color measurement instrument depends not only on price, but also on how well it meets your specific needs. For example, some instruments are engineered to endure the demanding conditions of the press room, while others are optimized for measuring thousands of patches for printer or press characterization. Let's look at various print needs and the instruments that can meet them. Let's start with densitometers. Densitometers have been used for years. They measure the density of ink, indicating how dark the ink appears, which correlates with ink film thickness, an essential factor in controlling color on press. However, densitometers only determine whether the ink color appears to be cyan, magenta, yellow, or black, and how dark it is. They cannot measure color accuracy in LAB values. This means that if an ink is contaminated, it can hit the target density, but still produce incorrect color. Entry-level densitometers provide density measurements and metrics like tint value, also known as dot area, and tone value increase, also known as dot gain. Advanced densitometers include additional measurements like overprint trapping, print contrast, and hue error. Let's move on to spectrophotometers and spectrodensitometers next. A spectrophotometer, such as one of the Exact 2 models, goes beyond the capabilities of a densitometer, providing colorimetric data for color matching and quality control in situations where accurate color reproduction is essential. It compares the printed ink's color to the specified LAB target values, helping operators assess the color difference known as delta E. Print buyers, especially those with strict brand color requirements, often specify acceptable delta E tolerances. Unlike legacy methods relying on target densities for CMYK inks, modern print standards focus on achieving LAB target values. Some standards also call for measuring overprints and gray balance patches. In practice, combining both density for process control and LAB for color accuracy can deliver optimal results, ensuring consistent and accurate color reproduction. X-Rite Best Match is a powerful tool to achieve this, designed to target LAB values, factoring in the specific ink and substrate being used. It provides users with guidance on density or ink strength adjustments to achieve the closest possible delta E match, ensuring optimal color accuracy. For those requiring advanced measurement capabilities, the Exact 2 Plus goes a step further. In addition to the metrics that the Exact 2 provides, the Plus model can evaluate substrate whiteness and brightness, ink opacity, metamerism, and can display spectral reflectance curves, making it ideal for quantifying and controlling color in the ink room as well as the press room. Now let's focus on color bar scanning solutions. When selecting an instrument, it's also important to consider the number of samples you need to measure and how the data is presented. Effective press control is achieved when the operator has a clear understanding of how the press is performing for all ink colors. In many packaging applications, particularly on web-fed presses, short control bars are placed at various locations on the form. The Exact 2 instruments feature integrated scanning wheels, enabling users to quickly scan across color patches for faster data collection. This reduces the time spent on measurement, allowing users to quickly get to the color analysis and correction. When used with color analysis software, like ColorCert or Measure Color, a quick scan of a control strip provides instant results on a dashboard, allowing operators to efficiently identify any conditions that require attention. On an offset press, The operator needs insight into each ink key's performance. The color bar has patches placed across the width of the press for evaluating all the metrics we've discussed. To address these needs, a cost-effective automated solution to measure the full color bar is the Exact Autoscan track, which uses a laser sight to align patches across sheets, up to 40 inches wide. For ultimate productivity, the IntelliTrax 2 features a look-ahead camera that automatically locates the press sheet color bar, eliminating the need for manual intervention. Both solutions utilize advanced software to monitor and display the performance of each ink zone, enabling quick and precise adjustments to the ink keys for accurate color corrections. For even greater efficiency, the Exact Autoscan and IntelliTrax 2 can be seamlessly integrated with a closed-loop press control system. These systems automatically and continuously adjust the ink keys based on real-time measurements, significantly reducing make-ready times and ensuring tighter control throughout production. The instruments and options we've discussed so far are specifically designed for ink and print production. Built to withstand the demands of production environments, these tools are rugged and ready for continuous use throughout the day. On the other hand, there are instruments tailored for prepress applications, such as the i1 spectrophotometers. These devices excel at measuring a vast number of patches, sometimes thousands, on specialized charts used for tasks like calibrating press curves or periodically calibrating and profiling inkjet printers to simulate production printing conditions. Think of these instruments as the sports cars of the color measurement world: fast, precise, and agile, but not built to endure the wear and tear of a production floor. All these instruments we've discussed so far share a common measurement geometry known as 45-0. The first number indicates the angle of the light source, in this case 45, while the second number, 0, represents the angle at which the reflected light is measured. This configuration mirrors how print should be viewed in a standardized viewing booth. The reflected light is filtered into precise increments across the entire visible spectrum, allowing it to be plotted as a spectral reflectance curve. By recording the reflected light energy at intervals across the visible spectrum, a spectrophotometer can, in essence, see how much color there is at each wavelength. So, in this example, when we measure this red, each filter results in a recorded number. When plotted against the visible spectrum, the recorded data shows a peak in the energy levels within the yellow, orange, and red regions of the spectrum. This is the signature of this measured color. Every color has its own distinct signature, and the best color match occurs when the spectral curves of the measured sample closely align with those of the stored standard. This spectral data can also be used for calculating accurate density values for all ink colors, including spot color inks. In 2009, ISO 3664 and 13655 were updated to provide better agreement between users' visual color observations and the differences reported by instruments. Instruments manufactured before 2009 did not meet these requirements. Let's take a look at why that matters. In 2009, ISO 13655 introduced the M modes to define different measurement conditions, creating a standard for consistent color measurements. In North American print production, the two most relevant modes are M0 and M1. M0 represents a legacy condition. Before 2009, specific measurement parameters, such as how instruments handled UV light, were not well defined, leading to variations between manufacturers. M1 addressed this by standardizing requirements, including how much UV light must be present during measurement. This was particularly important for accurately measuring paper stocks containing optical brighteners, which have become increasingly common in production workflows. As for M2, it's a UV cut condition. This mode filters out all reflected UV light and is often used in digital printing or applications where UV light must be excluded. However, this is not typically used in packaging. M3 is less common in North America, but is widely used in offset litho printing in Europe, particularly for measuring wet ink. It is typically used on presses with inline measurement systems that control ink keys. There may be instances when you need your handheld device to align with the inline press controls for consistency. If your substrate doesn't contain optical brighteners, the choice between M1 and M0 becomes less critical. Many packaging materials, for example, do not include brighteners. In these cases, the LAB values remain consistent across all three M modes. Additionally, the substrate will appear identical under ISO-compliant D50 lamps with or without a UV cut filter. This graph highlights how optical brighteners amplify light energy in the blue range, making the substrate appear brighter. When printing on substrates with optical brighteners, the choice of M mode becomes crucial. Notice that the LAB values differ across the M modes. M1 aligns with the latest ISO 3664 viewing booth standards, where substrate with optical brighteners appear slightly brighter and bluer under updated D50 lighting. In these scenarios, it's essential to match the M mode to the specified print standard or the customer's requirements to ensure accurate color reproduction. ISO standards for print measurement and process control are critical for consistency and quality. Deviating from the specified standards can lead to unacceptable results, including work that might seem acceptable to you, but is ultimately rejected. To ensure success, all instruments and software must be properly aligned with these key requirements. When looking at M modes, M1 is the preferred standard due to the technical advantages outlined earlier. It is also incorporated into ISO print standards for 4-color process inks. However, due to the legacy of M0, many custom spot colors were originally created using this method. As a result, M0 continues to be commonly used for measuring most spot inks at present. It's important to note that the standard viewing condition is D50 with a 2-degree observer. Alternatives like D65 or a 10-degree observer, which were used historically by some, are no longer recommended. Additionally, Delta E2000 has become the most commonly adopted color difference method in North America and should be your default method. Now there are some special cases out there for measurement. For example, printing directly on foils or metallic surfaces without an opaque white ink backer presents unique challenges due to specular highlights, where the surface reflects light in a highly directional way. Accurately measuring this type of color requires a specialized instrument capable of capturing the color with or without the specular highlight. This is what it looks like when the light is reflecting off the metallized material. You can see its intense specular highlights. Now, a standard 45-0 instrument struggles in these situations because most of the light hitting the surface at a 45-degree angle is reflected at the opposite angle, missing the instrument's optics entirely, and will measure as very dark. So that's where we need a sphere instrument, known as D8 sphere geometry. D stands for diffuse light, which is achieved when a baffle disperses the light by reflecting it off the white walls inside a sphere. The term 8 degrees refers to the angle of the sample port during measurement. Measurements can take two forms: spin, which includes the specular highlight or gloss, and SPEX, which excludes the specular component, allowing it to escape. Although the print industry currently lacks ISO standards for measuring colors under these specific conditions, emerging best practices are gradually being adopted. In some cases, brand owners may set specific requirements for color matching, particularly when using a sphere spectrophotometer. The last topic I want to cover today, before we take questions, is how to ensure your instruments measure accurately and consistently, which requires regular validation and performance checks for your instrument. Here's how you can ensure optimal results. First, proper cleaning is essential. Always follow the manufacturer's instructions to keep your instrument performing at its best. Alongside this, dust control is key. Be sure to keep the instrument, calibration tiles, and measured samples free of dust to avoid inaccuracies. White tile calibration is another crucial step. Your instrument or software will prompt you to recalibrate periodically throughout the day using the provided white tile. For sphere instruments, an additional calibration is performed using a black trap for enhanced accuracy. Next, monthly profiling with Net Profiler provides a comprehensive calibration process. Using a series of colored tiles, Net Profiler validates the instrument's accuracy and applies correction adjustments if needed to align with the factory calibration. If the instrument cannot be properly calibrated, Net Profiler will alert you immediately that service is needed. Finally, don't forget about annual factory certification. Sending your instrument back to the factory for extensive testing and certification ensures it continues to deliver precision year after year. All right, let's take some time to address the questions submitted during the webinar. If you haven't sent in your question yet, feel free to use the chat function to do so now. I'll cover as many as possible, but if we don't get to yours today, an X-Rite color expert will follow up with you directly. Additionally, if you'd like to speak with someone about your specific color evaluation needs, a survey will appear right after the webinar concludes. All right, the first question we received is, sometimes I measure a color, and it is in tolerance, and it looks good in my viewing booth. However, the customer complains that it doesn't match their other products with the same brand color under store lighting. What is going on? This may be the phenomenon known as metamerism, where a standard and a sample may appear to match under one lighting condition, but look very different under another. To detect this, you can compare the spectral reflectance curves in your spectrophotometer or software. If the curves intersect more than 3 times, it suggests that a match under D50 lighting could fail under other conditions. This mismatch often occurs when an ink is formulated solely to match LAB values, while more advanced formulations aim for a closer match across the spectral curve. Additionally, the metamerism function in the Exact2 allows you to measure the delta E, or color difference, across up to 3 different lighting conditions, providing a more comprehensive view of color behavior in different environments. All right, the next question we received was, what aperture size is required for print and packaging applications, especially when measuring dot gain patches? This is a great question. Aperture size is crucial for capturing tonal variations in screen tints accurately. In print and packaging, the aperture must be large enough to gather a representative sample of the printed screen tint. For instance, for print with over 133 lines per inch, a 2 mm aperture is sufficient to capture the tonal variations accurately, with a minimum patch size of 3 mm. Ideally, a 4 to 5 mm patch size is recommended for easier target placement. For prints below 133 lines per inch, a 5 to 7 mm patch is required, and a 4 mm aperture is needed to ensure an accurate measurement. Moving on to the next question, I need to match Pantone colors. What M mode are those standards? So that is a very important consideration. Pantone standards that are included in all X-Rite tools and licensed third-party tools for print QC are available in M0, M1, and M3. M2 is not used in packaging. Some design applications use M2, and that may work well for some digital inkjet printing with high OBA, optical brightener agent, content. A common mistake is to take the M2 LAB values from their design application and use it in production. Those values will not provide accurate results. The next question asks, are there any special considerations for measuring color on film substrates? Yes. There are 2 key considerations. First, some films exhibit surface characteristics resulting from the extrusion process, which can cause measurement variations depending on the instrument's orientation. The Exact2 can be configured to compensate for these variations. The Exact-XP is specifically configured for measuring films, while the Exact2 Plus allows users to configure the instrument with or without a specialized filter to address these surface effects. Secondly, when measuring white or clear films, opacity becomes a critical factor. These substrates allow significant light transmission, which can cause the underlying white backer material to affect the measurement. To ensure accurate readings, it's essential to use an ISO-compliant backer. One recommended option is the Munsell backer, available from X-Rite. All right, this is the last question I'll get to today. It says, I print to G7 gray balance. What instruments should I use? The Exact 2 supports all the essential measurement metrics required for G7 compliance. Additionally, the Exact Autoscan Pro and IntelliTrax 2 Pro are both G7 press control systems, certified by IDEA Alliance to monitor and manage compliance metrics with precision. For those questions I didn't get to today, an X-Rite color expert will be in touch soon. This concludes the webinar. Thanks again for everyone's time, and please stay on for a quick survey. Have a great day.